Hi, thank you all for coming, and I hope you're having a great day listening to all the presentations. Quick introduction. My name is Dion Mariyanayagam. Last year I finished my undergraduate degree in computer systems engineering with the first, and now I'm doing my PhD in polymorphic security for IoT. Before we start the presentation, please note that this is my final year project that I'm presenting, as it has been a catalyst for my PhD. If anyone has any questions, please do ask them at the end of the presentation, as some of your questions may be answered in the later slides. So, let's begin. Here's a quick overview on how the presentation is structured. My final year project is a smart, secure and sustainable robotic hand. But what does that mean? The robotic hand is a wireless Internet of Things device, which has two main parts to it: the robotic hand itself, and the glove, which controls the robotic hand by mimicking the user's hand movements. On the server side, which is the glove itself, the hand movements are captured using flexible sensors on each finger and a gyroscope to capture the rotation of the forearm. All the raw data from these sensors are sent in real time, filtered to reduce noise and anomalies, then encrypted and sent over to the client, which is the robotic hand, to execute the commands. There are some limitations because I'm using a microcontroller, therefore I need to use more lightweight solutions. At London Met, I learned a lot from various projects and modules, such as advanced electronics that gave me an in-depth look into circuit design, simulation and filtering, data acquisition and interfacing, and microprocessors and embedded systems, which helped me further develop my C programming language and understand how to interface various sensors and actuators. Additionally, distributed and internet systems, which really gave me an in-depth look on how clients and servers all communicate with each other and how to actually encrypt those communication streams as well. However, it really did come down to the skills that I self-taught. For example, 3D printing, 3D modeling, C++, MicroPython, PCB design and PCB manufacturing. All of these things that I learned in my own time. The robotic hand is 3D printed, and I use something called a wood-based PLA, which is 60% PLA and 40% wood fiber. I bought this filament from a UK company called Filamentive, based in Bradford, who make a filament from post and pre-consumer recycled materials. Now, PLA is a bioplastic that developed from plant-based sources, therefore is sustainable to produce and is biodegradable within industrial composting plants. Additionally, the nature of 3D printing allows for a quick turnaround time with low costs and tailor-made designs for consumers. Nonetheless, the novelty of this project really does derive from the security side of things, as it can execute commands with real-time encryption and decryption. Why should we encrypt robotic hands or even IoT devices in general? Well, robotic hands currently are used in the manufacturing industry to move heavy objects. Within this closed network environment, cybersecurity is not the most prominent concern, therefore not implemented. Technology, I'd argue, right now is between the second and third figures here, as it's our tool that gathers data about our habits, our likes, our dislikes, our buying patterns, the places we visit, both digitally and physically. So this builds a perfect digital profile of us that is really good for marketing and advertising through targeted ads. Eventually, as technology increases, the amalgamation of humanity and technology will occur with more complexity with embedded biotechnologies, and the data that is gathered is no longer going to be our habits. This notion is going to be changing into gathering data about our biology. It's more into like wearable technology and also biochemistry as well. Even though a company may know your biology or your biochemistry, this change is not as dystopian as it seems, as health industries can really benefit from precise medical information. Therefore, your experiences and reactions to certain situations and stimuli makes you a data goldmine, a great baseline tool to model artificial intelligence and machine learning. So you and your data is valuable, and anything that is valued should be protected. Hence why I conclude that the robotic hand or any data that is valued should be under some sort of encryption and protection. Now we will move on to how the system works. So this is the top-down approach for both the server and client components. We'll first start with the client. Here we have all the components required for the client to work, which is the microcontroller, which is called the ESP32, servo drivers, which move all the motors and servos in order to bend the fingers and rotate the forearm and also the thumb. We also have a status LED to say when it's connected or not. We have a power module to transition power to the servo driver and the actual microcontroller itself. So the power is split from 5 volts to 3 volts. So that's pretty much it for the client side of things. Now moving on to the server side, which is the glove. The glove is a lot more simple, whereby we have flex sensors to collect the data on the bend of each finger, and the gyroscope to detect the rotation of the forearm. For all the 3D models, I printed using an FDM 3D printer. I also used 2 ESP32s for the client and server. This is because it has inbuilt Wi-Fi, so I just reduced the number of components I use. Lastly, the client and server are using an asynchronous web server. This I'll go into more detail in the coming slides. Now, the communication stream is fully encrypted on top of the SSID and password as well. For the 3D modeling, I used Blender, but I designed most of the models using SketchUp, which is the free software. You can see it being 3D printed in the video below. The server is an asynchronous web server and publishes its encrypted data to unique URLs, like index finger. So the client can connect to it, get that data, and then decrypt that data, and then execute the command. So we can see here that the server starts, you have the raw data from the actual fingers. Those readings are then encrypted, and then you send that data over to the client. The client uses a common encryption key to decrypt the actual raw data. That raw data is then turned into a command to execute. Here we have the construction of the robotic hand. The limited number of modules really benefited the design as there was less wiring. There's only really 3 main parts to it: the power module, the servo driver, and the ESP. I also have a status LED just to show that the client is connected to the server. The way the servers actually move the robotic hand is through fishing wire because of its high tensile ability, so it will not snap over time. The encrypted communication stream between the client and server is achieved by XOR encryption, as its real-time encryption is super lightweight for a consumer-level microcontroller, and it doesn't cause a huge lag between the user moving their finger and the robotic hand replicating it. More advanced encryption like AES and scrambling techniques will sacrifice performance. This is because the microcontroller is being used as a server, gathering raw data from the sensors, filtering the data through signal processing, and encrypting it. Testing was a continual factor for this project, and for the 3D printing side of it, I had to test a lot of different properties. And what ended up is these different values for these different properties. This is optimized, this is the most optimized approach for cost effectiveness and the strength of the 3D print. For the flex sensors, as soon as the flex sensor is bent, it will then generate a certain amount of readings, which will then translate to how much the actual servo will bend a finger. So the way I calculated this is by bending the flex sensor to a certain amount of degree and then calculating the pin reading of that degree. With that, I can map out exactly the degree of bend versus the valued output. Now for the gyroscope was a bit different. The way I calculated the gyroscope is that I laid it flat first, and by laying it flat I know there's not going to be any kind of movement. Then what I did is I did a reading without it being filtered, so you can see that's the orange here, and then I did the same reading again, but this time using a filter on top of it, so just smoothing out the entire process. So the closer to 0 the better it is. So you can see that the blue, which is the filtered version, is closest to 0 and it is the better output. After doing the initial testing for the flex sensors, I could then put it into practice. So I put it on the glove, and as you can see when I bend the finger, the value increases. So I did this for every single finger, so we can read the actual movement for the entire hand. Here is the high-level logic of the client and server. So we will start with the server first. As you can see, as soon as the server starts, we start the Wi-Fi and then we begin a loop. That loop essentially reads the data for the flex sensors and the gyroscope. So you're capturing the hand movement. This is then filtered, as we saw in the slides before. It converted to degrees, and then we encrypt it. And then that is stored in the unique URLs. That loop is then done again, so then we can capture the most recent hand movement. So that's how the server works. And then in the client, which is the actual robotic hand itself, we begin the server driver, so we get all the servers prepared. We then connect to the actual server using a Wi-Fi, and if that's connected, we then put the status LED on. It's just the easy way to see if it's connected or not. And then we begin a loop. This loop is reading the serial and getting the HTTP request. This request is for the unique URL here. So each finger then moves each servo on the actual cybernetic hand. Now you can see that here, the unique flex sensor, the gyroscope. So as soon as we get that message, we then decrypt it using the common encryption key that we have. And then once it's decrypted, that is then a command that can move a unique servo or the forearm itself. One of the most important testing that I did was the testing of different ciphers. So I tested XOR, ROT47, ROT13 and Caesar. Now the entire process of this is to find out which one is the quickest. Therefore, there is no lag between the person moving their finger and the robotic hand replicating that movement. So after doing some experimentation, I found out that the quickest one is XOR, but we can see that there is no huge difference between no encryption and XOR. There's only around 5 milliseconds. But you have to realize the more complex that these systems become, the more lag it produces. So luckily, this raw data is not too complicated for these ciphers to actually encrypt. So in this graph here, time complexities, this takes everything to regard. It takes in the actual server encrypting the data, the time it takes to transmit the data to the client, and the time it takes for the client to decrypt the data. So this is the total time for all of that. In this side here, in this graph here, this is just the how fast it encrypts and how fast it decrypts, and this side is measured in microseconds compared to this one, which is measured in milliseconds. So you can see that it's the transmission time that takes the most, and is not the actual encryption side itself. After doing all the various testing, I put everything together, and here is a video about the unencrypted version and the encrypted version of it. So the unencrypted version, you can see in the bottom where the numbers are represented, and these are the raw numbers that you're seeing. So as soon as I move my hand, you can see that there's an increase of numbers, which is the degree of bend for the finger. Now for the encrypted version, I'm using buttons instead, just to show a visual representation of the difference. And you can see here that it's no longer numbers, but it's actually letters. This is because it's being encrypted using XOR, which is the fastest encryption that I found using my testing. To conclude, we presented a bespoke solution to the design and control of a 3D printed robotic hand that allows for a cost-effective, lightweight, real-time, and secures data communication streams between the server and the client. Potential applications are in areas such as psychotherapy, controlling operations in hazardous environments, motion models for cinematography, and also immersive virtual reality environments. Lastly, for future projects, I'm currently pursuing my PhD research on the topic of lightweight polymorphic security systems for IoT devices. I'm working with Professor Bao and Dr. Shukla to incorporate all of this. And I've been working on a rescale project to make a local air quality monitoring system, which won the Big Idea Challenge for the climate change category. And this summer I'm planning to capture some data using sensors in high altitude by using a weather balloon with some of my friends as well. So if you have any questions about any of the topics talked about today, please do ask away. And if you want to email me, you can find that in the beginning of the slide as well. Thank you for listening, and I hope to hear from you.